Today we have a problem. We roll a fair die repeatedly until we see the number 4 appear, and then we stop. The outcome of the experiment is the number of rolls. Part A asks us to describe the sample space omega and the probability measure p to model this situation. And Part B asks us to calculate the probability that the number 4 never appears. So before answering this question, I'd ask you to pause the video and attempt to experiment on your own for Part B. I would be interested to see that if any of you are able to roll a die repeatedly and never encounter the number 4. I would be very impressed. No, okay. So comment in the comment section, how many rolls did it take you until you saw the number 4 appear? Okay. All right. So for Part A, we're supposed to describe the sample space and the probability measure. Remember, the sample space is the set of possible outcomes, and the probability measure is a function from the power set of the sample space into the real numbers, which satisfies certain axioms. Namely, we want that the probability of any event E is between 1 and 0. We also want that the probability of the total space is 1, so something is guaranteed to happen, and the probability of the empty set is 0. And finally, we are going to require this property of what's called additivity, or countable additivity, which means that if AN is disjoint, is some family of events which is disjoint, pairwise, then the probability of their disjoint union is the sum of the probabilities of each individual event, okay? And I covered this more in depth in exercise 1 in this kind of series of videos. Now, let me just quickly note, this is a function from the power set of omega into the reals. For those of you who are not familiar with the power set, that is just the set of all subsets. And any subset of the sample space is called an event, and an element of the sample space is called an occurrence or an outcome. Okay, so to describe the sample space, we need to describe the set of possible outcomes. And so the outcome is that it's given to us here. The outcome of the experiment is the number of rolls, okay? So that makes our job fairly easy. So omega is just the set of natural numbers. So 1, 2, 3, 4, etc. Okay, and this is often denoted with this black letter bold N. So omega is just the number of rolls that it takes us to see the number 4 appearing. Now notice that this is the number of rolls, not the outcome of the dice roll. So number of rolls until we see a 4. And then I suppose that in the hypothetical world where someone could keep rolling the die forever and never see a 4, we actually need to include that possibility in our sample space. So let me include that as infinity. Okay. So infinity is the outcome that, in fact, we roll the die forever, we grow old and never see a 4, and we've been rolling the die our whole life and never see a 4 appear. And and then somehow we're immortal and we live forever, and still it never appears. So clearly that's very unlikely, as we're about to rigorously prove. But we still need to include it, technically speaking, into our sample space. Now our probability measure, P, this is the interesting part of the exercise here. So P applied to N, this is the probability in words, the probability we see no 4 in the first n-1 rolls, and then observe a 4 on the nth roll. Okay, that's in words. Now what about mathematically? So in order to not observe a 4 in the first n-1 rolls, well, in a single roll, the probability of not observing a 4 is 5/6, considering we have a fair die. So there's a 5/6 chance that we do not observe a 4. So for this outcome to happen n-1 times consecutively, we need to raise 5/6 to the n-1 power. And then finally, observing a 4 on the nth roll, well, when I take my nth roll, there's a probability of 1/6 that I observe a 4. Okay, wonderful. Now, if you go back to my video on exercise 1.8, there was a nice discussion of why these probabilities multiply in this way. And just to summarize real quickly for you, for those who are interested, the reason why these probabilities multiply is because let me choose a different color here. So if I view each dice roll as essentially branches of a tree in a universe of possibility, then every time I roll a die, there are 6 possible outcomes. And so essentially, I have a tree with six distinct branches, which we can label 1, 2, 3, 4, 5, 6. And these branches correspond to the outcome of the first roll of my die. Now, if I roll a 4, I'm done, so the tree essentially dies. But if I don't roll a 4, then I'm going to roll the die again. And then at this stage, the tree splits into another 6 possibilities. And so you can see that in moving along the possible branches, we're essentially counting the number of branches of this tree which satisfy this property. And the number of these branches, well, at each stage of my branch, I'm going to be splitting off into 6 new branches, and 5 of those are precisely the ones with no 4s, and then one of them is the branch with a 4. So this is essentially a way of counting the number of branches in a whole tree, which represents all possible outcomes of the experiment. And the multiplication is just coming from the fact that at each dice roll, each branch of the tree is splitting into 6 new branches. And that process is a multiplicative process. Okay, so that's why the probabilities multiply in this way. Wonderful. So now we have our probability function. We have specified the probability for a single outcome. And recall that specifying the probability of a single outcome, if I specify the probability for all possible outcomes, then that is actually sufficient to fully specify the probability measure, because the probability of any event, so the probability of any event, let me just note this here. So if E is a subset of omega, so it's some event which consists of a family of possible outcomes, then E is going to be some countable set of natural numbers, let's say E1, E2, etc. And this is a subset of the okay, let's just say omega, but omega is secretly the natural numbers union with infinity. Then this is actually just a disjoint union of different outcomes, okay? Namely, this is just the disjoint union from I equals, let's say, 1 to infinity of EIs of all the outcomes. And so by my axioms of probability, I know that the probability of E occurring is simply the sum of the probabilities of the EIs, each individual outcome belonging to E. And even if E was a finite set, this formula would still hold, but the sum would then be finite, okay? So I'm going into this nuance to just tell you that, in general, the probability measure is a function from the power set of omega. It's not a function from omega to n. However, since omega is a countable set, we need only specify the probability on the singleton sets, or the outcomes, and then once this is specified, we automatically have the probability measure for any subset of omega, which is given by this formula, okay? So if that doesn't make sense, please let me know in the comments, and I'll try to explain it better. All right, so this solves part A. Now let's move on to part B. So part B is essentially the missing ingredient that I swept away in part A, which part B is just the probability of this infinity observation, right? I kind of swept that aside underneath the rug in part A. And so now it's time to lift up the rug and not sweep it under the rug anymore. So now, if I look at the probability of infinity, how would you calculate this? Well, if this event actually occurs, that means that I essentially observed no 4 on the first roll, no 4 on the second roll, no 4 on the third roll, etc. So I actually have every roll I've observed an event with a 5/6 probability, okay? And that's occurred all the way out to infinity. So this is actually just the infinite product from I equals 1 to infinity of 5/6. Okay? Which is just fancy math notation for 5/6 multiplied into itself an infinite number of times. And this, by definition, is the limit as n approaches infinity of 5/6 to the power n. Okay? And since 5/6 is a number that's smaller than 1, this limit is 0. Okay. Yeah, so any number, when I raise it to an nth power, if that number is less than 1, then this value will decay to 0. Now, one could prove that using calculus, so let's quickly prove it using calculus. So I write this as 5 to the n over 6 to the n. Okay, and now, okay, so if I, for a moment, assume that the limit exists, which is not necessarily a fair thing to assume, but if I assume that it exists, then let's suppose it's equal to something called L. Actually, we can actually keep it to the power n. That's actually fine. So then what I'm going to do is I'm going to take the logarithm of both sides of this equality. So when I take the logarithm then because the log is a continuous function, and notice that L is certainly greater than or equal to 0, okay? So when I take the logarithm of this inequality, I'm going to get n log of 5/6 is equal to log L, okay? And now taking the logarithm and then looking at the limit as n goes to infinity, okay, then the idea is heuristically that as n goes to infinity, this quantity is approaching negative infinity because log of 5/6 is negative. And so we get that the log of L is equal to negative infinity. And then if I exponentiate both sides, I'm going to recognize that L is equal to 0. So honestly, this is kind of a very gross argument. If this argument makes you upset, I empathize with you. It also makes me upset. Let me try to come up with a better argument, okay? So what would be a better way to argue this? Okay, I have an interesting idea. So if we look at 5/6 times 5/6, this is going to be less than or equal to, I can replace 5/6 with a bigger fraction. Let me replace it with 6/7. Okay, so 6/7 is a bigger fraction than 5/6 because 1/7 is smaller than 1/6. So this inequality is certainly valid, but this number on the right-hand side is actually easier. This is 5/7, okay? Aha, so now I have a nice kind of trick. So now look at if I have 5/6 times 5/6 times 5/6, then I can replace this 5/6 with a 6/7, and then this 5/6, let me replace it with 7/8. And then if I keep doing this, I'll realize that in fact, 5/6 to the n is less than or equal to, inductively speaking, 5 over 6 plus n. Five plus n, sorry. 5 plus n. Just quickly verify, when n equals 2, I have this inequality with 5/7. When n equals 3, I have the inequality with 5/8. So this looks correct. And now, with this inequality, I have a nice way of showing that this number goes to 0, just because I know that 5 over 5 plus 5 over n goes to 0. This goes to 0 as 1 over n. I could just even go one step further and say 5 over 5 plus n, well, this is going to be less than or equal to 5 over n, since 5 plus n is bigger than n, and it's in the denominator. And 5 over n, well, we know that 1 over n goes to 0 as n goes to infinity. Yeah, and the reason why we know that is because, watch my Foundations of Analysis videos. No, but the reason why 5 over n goes to 0 is because of basically boils down to Peano's axioms of the natural numbers. And here we're getting into the mathematical weeds, but essentially it will boil down to essentially Peano's axiom of the natural numbers. So it's an axiomatic fact, this quantity goes to 0 as n goes to infinity, which proves that this limit is in fact 0 in a much more rigorous way than this whole logarithm sorcery nonsense. Now, let me just prove this in a different way, because even this is a little bit unsettling, and this is not even ideal as it is. So let me just return to the axioms of probability, which state that the probability of two disjoint events sums through the union. So if I add the probability of not infinity, so the probability of observing anything in the set 1, 2, 3, 4. Okay, so if I look at the event where it takes me an infinite number of rolls and its probability, and add to this the probability of having a finite number of rolls, it could be any number, but just a finite number of rolls, well then this constitutes a partition of the entire space. Namely, it constitutes a set of two events whose union is the entire space. So infinity union 1, 2, 3, etc. is the whole space. And furthermore, these sets are disjoint. So infinity intersect this 1, 2, 3, etc. set of all finite numbers. This is equal to the empty set. So what this tells me is that by the axioms of a probability measure, by the very definition of P, this probability needs to be the probability of omega, or in other words, it needs to sum to 1. Okay? Wonderful. So now, this tells me that in order to understand the probability of infinity occurring, I need to understand the probability of, I only need to understand the probability of observing a finite number of rolls before we see a 4. Okay? So the probability of this set, 1, 2, 3, going on, okay? So as we discussed previously, this is just, I can write this set of natural numbers as a disjoint union over all the singleton sets, which are just the n's, where n runs from 1 to infinity, okay? And now, this is just a disjoint union of the possible outcomes, where n is the finite number of rolls. And then, again, by the additivity of the probability measure, this disjoint union turns into a sum. This is the additivity property. And so I get this following expression. Okay, and now I know the probability of n. We calculated that in part A. So this is going to be sum from n equals 1 to infinity. And then I have 5, 6 to the n minus 1 times 1, 6. Okay. Well, now I just have a geometric series. Okay? And this geometric series is going to sum to its first term. The first term, if I plug in n equals 1 into this guy, I get 1/6. So the first term is 1/6 divided by 1 minus the common ratio. Common ratio is 5, 6. It's a geometric series. Aha, but 1 minus 5, 6 is 1/6. So I end up with 1/6 divided by 1/6, which is equal to 1. Okay, so I'm going to cover geometric series in the Foundations of Analysis course. Hopefully you've seen it in calculus before. If you haven't, then this is going to be quite difficult to understand. And I'm not going to cover this in full depth because it's outside of the scope of this video. However, stay tuned, because in my Foundations of Analysis series, we'll definitely be covering things like geometric series in rigorous detail. Okay, so again, this is just the formula that the sum, let me just write the formula, the sum of a times r to the n, okay, where n is equal to 0 to infinity. So essentially, a is the first term of the geometric series, r is the common ratio. This is equal to a over 1 minus r when the absolute value of r is less than 1. Okay, otherwise it diverges. So in this case, since 5, 6 is less than 1, we get this formula. And what this ultimately tells me is that this probability is 1. And so I have the probability of infinity occurring plus 1 is equal to 1. So subtracting 1 from both sides, I'm left with the probability of infinity occurring is precisely 0. So therefore, if the theory of math is correct, then it should be impossible for you to roll a die and just keep going on and on forever and never get the number 4. But don't trust math. Try it at home. Try rolling a die, a fair die, and see if you never roll the number 4. Okay. Anyways, have a nice day. Bye.